The word entropy actually comes from the Greek, I found out. It comes from entropia, which means turning toward or something of that type. Transformation, something like that. And what it describes in thermodynamics essentially is a measurement of randomness, as bizarre as that sounds. The units of entropy, as we see here, are joule per Kelvin. So it's how much energy there is per amount of temperature available. That's going to play an important role later when we start to distribute molecules into various energy levels based on the amount of ambient energy they have available. Now, just like we learn for internal energy and we learn for enthalpy, entropy is extensive, which of course means it scales with the amount of matter present. Also, entropy is a state function, as I show there, that essentially, as long as you know the beginning and starting place, which is very important, you can calculate the entropy change independent of path, meaning there could be a gazillion things going on in between you going from the initial point to the final point, but we don't really care about all the nuances and details of all those intermediate stops along the way. We only need to know where we start, where we stop, and then we can just get the total change along any path with any number of intermediates by taking the difference between the final and the initial. Okay, so as I said, it measures in some way the degree of randomization, and if ds is greater than 0, processes are randomizing, and if you make a numeric measurement of ds that is less than 0, that's really the randomization process in reverse, if you like to think of it in a chemical sense, and that would be doing an ordering. A little on the historical perspective of entropy. First of all, the name entropy came from entropy, as I said, and was given by Clausius, who we'll mention prominently later on. Probably the original calculations, numeric measurements of things of this sort were done by an individual by the name of Carnot, who we will look closely at as well further down the road. And he did so in a treatise, as we say there, titled Reflections on the Motive Power of Fire, which is a translation from French, as a matter of fact. And the little cartoon in the center of the page is showing what would happen if I had a engine, a internal combustion engine, as we know them. Now remember, those were developed in the 1800s to power with steam before they were powered with gasoline, and this is an engineering discussion of the it's a scientific discussion of the engineering phenomenon, really. So scientists were trying to understand how work was being done by the combustion in the form of heat. Remember, heat is randomized motion of matter, where work is concerted motion of matter. So what Carnot concluded was that if you have some hot source of random motion at, as I say there, temperature T hot, we can remove Q hot from it. And through the machinations and magic of some engine, we will convert that motion in the random form into motion in the work form, and as we show in the yellow. Now the point would be that you cannot completely convert all the heat to work unless you have some exchange of the heat with what we call on the right-hand picture a cold sink. So you'll notice what I'm doing there is I'm removing some amount of heat. There's an endothermic process where a hot source is removing heat energy, transferring a piece of it to a cold body, and siphoning off a smaller yellow arrow of work. So again, here the point would be that you can't get all the heat transformed into work if you want the engine to run spontaneously. Remember, the first law still applies. Q hot, the heat removed from the hot source, has to equal the sum of Q cold and W. Q cold, of course, being how much heat is deposited into the cold sink. So the first law is certainly obeyed, but the point here is to run this spontaneously, you have to dump some heat into this cold sink in order that the process can just continue. Now, this was refined, as you can see, by William Thomson, who was later Lord Kelvin, into the so-called second law of thermodynamics. And when we typically think of the second law of thermodynamics, we typically think of it describing spontaneity. And really, the context in which it's written is a description of this idea of transfer of heat energy to run a spontaneous internal combustion engine. What we're going to do is partition the universe up into the system and the surroundings, as we have done in the past. And the system is the chemical process we're interested in. Essentially, the surroundings is everything else. So let's begin with describing the entropy of the easier of the two. That would be the entropy of the surroundings. Now, when we deposit heat into the surroundings, that heat is randomization deposited in the surroundings by the random motion of the heat. So we are naturally increasing the entropy of the surroundings by depositing heat in it. So as we see there, ds of the surroundings is proportional to dq of the surroundings. Now, if the system is undergoing an endothermic process, then the system would be taking heat from the surroundings. So dq of the surroundings would be negative. If the system is undergoing an exothermic process, it is dumping heat into the surroundings. So in a case like that, of course, dq of the surroundings is a positive value when the system undergoes an exothermic process. Now, if we then think about a total quantity of randomness that is generated by this removal or deposit of heat in the surroundings, we have to also take into account the temperature of the surroundings. Why? Well, just simply think about taking 10 kilojoules of heat and depositing it into a chunk of ice. That will cause a great amount of randomization to that chunk of ice based on the temperature that that ice is at. But now let's take 10 kilojoules of heat and deposit it into a fire. Now that will increase randomization in the fire as well, but not to the same extent that depositing that 10 kilojoules into a colder system would have generated randomization. So as we say there, we're going to remove the proportionality between the increment of entropy gained in the surroundings and the increment of heat deposited. We get rid of the proportionality by saying simply that ds of the surroundings is exactly equal to dq of the surroundings over T, where T is the thermal contact diathermic temperature between system and surroundings. So for instance then, again, if T is a big number, then of course ds is going to be a small number, where vice versa, if T is a small number, ds is going to be a much bigger number. Now remember, another thing, that temperature we're going to use, of course, is Kelvin. We're not going to use it as a relative measurement like Celsius or Fahrenheit. We're going to use Kelvin, which is the absolute measurement, which of course all temperatures are positive on the Kelvin scale beginning at 0 Kelvin. And notice if you deposit, as a matter of fact, any amount of heat into a body at absolute 0, you would produce an infinite amount of randomization of change. Now let's look at how we can write the entropy change in the surroundings as a function of what's going on in the system. From the previous slide, we concluded ds of the surroundings equals dq of the surroundings over T. The temperature we're going to assume in the surroundings and system is the same, so they're in diathermic contact with one another. Now, because the universe has been partitioned into dq of the surroundings plus dq of the system, and because our universe is isolated, remember isolated means it's adiabatic and closed as well, but since it's adiabatic, dq of the universe is 0, which sounds bizarre, but what that means is if dq of the universe is 0 and it is equal to dq of the system plus dq of the surroundings, then dq of the system equals minus dq of the surroundings. Now that's not really a stretch of our imaginations. Think about it. What we're saying is if heat is lost by the system, it goes into the surroundings. That's all we're saying. If heat is gained by the system, it had to come from the surroundings. There's just simply a sign difference between the magnitude of heat exchanged between the two bodies in thermal contact. So in conclusion then, of course, ds surroundings is equal to minus dq system over T. And if I do an isobaric or a constant pressure process, remember that dq is equal to dH, so I could write this constant pressure enthalpy of the surroundings in one of two ways, depending on which way I want to do it, depending on what information I have available. First of all, ds of the surrounding can either be minus dH of the system over T. We'll use that in some situations, particularly at phase boundaries. Or ds of the surroundings equals minus C sub P dt, which is equivalent to dH over T. Now, at the fixed temperature of an equilibrium phase transition, as I said, that's where we would use the enthalpy form of the expression. ds, I'm going to integrate on the left from SI to SF. I'm going to assume, now this is of course very common, notice I have the temperature factored out of the integral, which means that the temperature is constant, and notice I'm writing there minus 1 over T transition. Remember what I called this in the past. This is the latent heat, meaning you can't sense it. The temperature does not change during phase transition. When you're melting ice, the temperature remains at 0 degrees C until all the ice is melted. When you're boiling water, the liquid remains at 100 degrees C until all the water is boiled. So what we can say then is the entropy change at this phase transition occurs at a constant temperature of the transition point of boiling, with sublimation, whatever it might be. And then we can integrate the state function ds of the system from the initial to final enthalpy, and we get a closed form equation for the entropy change at a phase boundary. Now this equation, please note, only applies at the transition between two phases. So you have to be exactly at the transition point, the equilibrium point of, say, boiling, the equilibrium point of, say, evaporating, subliming, depositing, whatever other phase transition you might want. So this has limited application at those transition temperatures. Delta S surroundings equals minus delta H of the transition for the system divided by T of the transition. Now, if instead of being a constant pressure situation, you were working with a constant volume situation, then instead of the dq of the system is CV dt. So ds to the surroundings would be minus either du over t or minus CV dt over t. If we integrate at the phase transition, delta S of the surroundings would be delta U of the system divided by the T of the transition. Now, the forms involving the heat capacity we'll look at on later slides when we look at just heating or cooling substances without worrying about transformation from one phase to another. This slide is a reminder as to how we could come to the conclusion that for an isochoric or constant volume process, that dQ of the system is equal to du of the system. We would begin by the general expression of the increment of change of the internal energy. du is dQ plus dW. And of course, remember, du is a state function, path independent, while the other two vary depending on the conditions of the of a process that a system is undergoing. So the dQ plus dW always sum to the same number, just along different paths. They are varying, even though du is not varying. So if we use again the definition of dW is minus p dV, you'll notice I've made that substitution in there. And then if we choose an isochoric process, which means dV is 0, that says that du is dQ, which I'm now subscripting as V. And the reason I'm doing that is I've chosen a specific path. Along the path where volume is constant, du is the specific form of heat that is dQV. Now notice I didn't put a duV. Why? Because it doesn't matter how we design the path for du. It does matter for dQ. Okay, so since dQ is equal to C dt, but since I've specified constant volume as the form of that Q, I must say then that dQV is C sub V dt. Now really C sub V is an extensive, scales with the amount of matter, so I might wish to then put it in the intensive form where I'm writing this other CV as an intensive. What would be the difference there? That would be what I would call the specific heat if I'm a chemist. So now I would really have mass times specific heat times change in temperature to get the heat of the reaction in the bottom equation. On this slide, I'm really just doing the same thing, reminding us how we can show that in the isobaric or the constant pressure case, that dQ of the system is related to dH of the system. We begin with the definition of H as U plus PV, then dH is du plus dPV, and I have to use the chain rule to say that that is du plus PdV plus VdP. Then if I choose the definition of internal energy as dQ minus PdV, where I've substituted for work dW minus PdV, then put that into my increment of change of enthalpy, you'll notice I get a cancellation of the PdV terms in dH. So the dH is dQ plus VdP. Now, once you specify constant pressure, dP is 0. So dH is dQ at constant pressure. Now, once again, notice I've say dH on the left, but I put dQ sub P on the right because dH is a state function. It really doesn't matter what I do. I'm going to get the same dH whether I call it constant pressure, constant volume, whatever I do. But since Q is a path-dependent function, the value for Q along this particular path is different. And again, if I go from the definition of what Cp is, it's dH dt at constant P, dH is C sub P dt. A German by the name of Clausius, who studied entropy and the quantification of entropy, as a matter of fact, he's the one who coined the term entropy, he came to a conclusion as to how entropy works, or how systems must behave if they're isolated. And his conclusion was that for isolated systems, that for any actually occurring process, something that will happen in nature, ds must always be greater than or equal to 0. Now, the inequality is such that processes which are irreversible, that are going to naturally occur in nature, have a value of ds that is greater than 0. Processes which are reversible in nature, for isolated systems, have a ds equal to 0. Now, let's just then look at some relationships between this idea of reversibility and irreversibility here. For instance, if I was looking at how we can think of reversibility in a chemical system, the easiest analogy for what reversibility applies to is equilibrium. That's a kind of a tipping point. You're at a balancing point where really neither a forward or reverse process from that particular juncture is spontaneous. You're balanced. But it's a very delicate balance at equilibrium, as we're all very well aware. Any slight little Le Chatelier stress on the point of equilibrium, the system immediately begins to take steps to adjust to return to equilibrium. That's the indication that we're at this fine balancing point. Now that I've stressed it, I'm away from equilibrium, and I will have spontaneous change in the components present until I get back to that fine tipping point. As long as nothing perturbs it, things even in the form of heat, light, reactants, products, temperature, a wide variety of things can cause these tippings of equilibrium, but as long as nothing will perturb the system at that particular juncture, it will remain at equilibrium for all remaining time. Now, I show there in particular, because we're going to be using things like this just as a reminder, if I have an isothermal reversible expansion, I have dW is equal to minus PdV, and reversibility means that the internal and external pressures match exactly at all points. So I change my external pressure to the internal pressure, and if the gas is ideal, that internal pressure can be expressed as nRT over V. And so the work of a reversible process, as you see there, is nRT ln Vf over Vi. Now, as we talked about, this in expansion cases, this is the maximum amount of work a gas can do while it's expanding. If you go in the opposite sense, as bizarre as it sounds, upon compression, reversible compression is the minimum amount of work you have to do on a system in order for it to be to accomplish the compression. Okay, now if we do an irreversible process, that means that the pressure that we're exerting on a system is constant, whether it's greater than or less than. The internal pressure will really then decide which way the volume is going to go. If the external pressure is greater than the internal, then the VI will be greater than VF because it'll squeeze it in. If the external pressure is less than the internal pressure, then VI will be less than VF because the gas will expand outward. But in any event, the irreversible work, after factoring out this constant external pressure, would be minus P external delta V. So what we do is we use a trick of the Clausius inequality in order to be able to calculate the entropy of the system. Now remember, the entropy of the surroundings is minus dq the system over T. What are we going to do to find ds of the system? Well, remember, according to Clausius, for any naturally occurring process in an isolated system, ds is greater than or equal to 0. So if we choose and to define the universe this isolated system as some system of interest plus the surroundings. Of course, ds of the universe then is ds system plus ds surroundings, and of course, again, the Clausius inequality must apply. That is greater than or equal to 0. So let's just choose that we have a reversible process. Now, ds of the system reversible, moving ds of the surroundings to the other side reversible, you note I have ds of the system reversible is equal to minus ds of the surroundings reversible. So now what I'm just going to do is I already have a recipe to find ds of the surroundings. It was it was minus dq of the system over t. So then I can conclude by putting minus dq of the system over t into the equation that ds of the surroundings reversible would be minus dq of the system reversible over t. Now here's the real stickler, if you like. ds of the system reversible is a path-independent function. I don't care if it's reversible or not. So whether the process is reversible or isn't reversible, I can remove that stigma that I have placed on the left-hand side and just get rid of the reversible word and apply this equation to any process. However, on the right, dq is a path-dependent function. I don't have the latitude to remove the reversibility conjecture on the right-hand side. So here is the ultimate conclusion that Clausius drew. I can calculate the entropy change in the system, whether the process is reversible or irreversible. I can calculate whatever entropy that is by finding a reversible path, designing it, whether the system is undergoing a reversible action or not, it doesn't matter. The entropy change would be equivalent to as if it was going on the reversible path. Now again, if these processes happen to be isothermal, then if I have an ideal gas undergoing isothermal process, dq is equal to minus dw. So then that would be equal to minus the reversible work if I'm undergoing isothermal processes. We already mentioned things about whether or not the reversible work is at its maximum or minimum. And so you can see that upon expansion, you're going to be maximizing entropy because of the fact that you're going to put a reversible form of the work as Vf and Vi change, and Vf is greater than Vi. The reversible path of work is the maximum work, so that would correspond to giving me max entropy in that system as well. The opposite is true in the compression idea, as bizarre as it sounds. Remember, I claimed to you that the work along the reversible compression is the minimum work you need to do to compress that gas. So when I'm compressing gases, I'm going to minimize entropy due along that because I'm choosing that reversible path. Let's look at how this applies to the spontaneity of heat flow. Okay, so I have a cartoon here of an isolated system consisting of a hot object at temperature T hot in thermal contact with a cold object of temperature T cold. And of course the idea of spontaneity, and I think everybody here would say that Q flows from the hot body to the cold body. So the hot object cools, the cold object warms spontaneously. Let's see how that can be described according to Clausius. So I begin with the fact that ds in this isolated system has to be greater than or equal to the entropy change in the system and the surroundings, and those would be, it's just not the system and the surroundings. There is no such thing here. There's two systems, if you like. There's a hot system and a cold system. That's isolated. You could call one the surroundings to the other, whatever, it doesn't matter. But ds of this universe is the entropy change in both of those. That will be dq hot over t hot plus dq cold over t cold. So remember, of course, because the systems are isolated, the heat is exchanged between them, so dq hot equals minus dq cold. I'll substitute that into the first term and get ds is greater than or equal to minus dq cold over t hot plus dq cold over t cold. And I factor out the dq cold, and I get 1 over t cold minus 1 over t hot. Now, of course, dq cold is greater than 0. The cold body, well, let's just claim, maybe we shouldn't make that claim. Let's just say, let's suppose dq cold is greater than 0. Maybe that's a better way of saying it. If that is true, then ds will be greater than 0 as long as t hot is greater than t cold. Notice what I'm saying there. 1 over t hot is a smaller number than 1 over t cold, obviously. So the entropy will remain positive as long as dq cold is greater than 0. Okay, so if dq cold is less than 0, of course, that's exothermic, and of course, then the ds would be negative, and we're claiming that's non-spontaneous. So the spontaneous flow of heat is with dq cold greater than 0, because, of course, t hot is a bigger number than t cold. Now, what happens when d hot equals d cold? Then I will get 1 over t cold minus 1 over t cold, which is 0. And so that times any dq is 0, ds is 0. I'm at equilibrium. I'm at the tipping point. They are in thermal equilibrium with one another when they come to exactly the same temperature. So what we would claim thermodynamically, entropically speaking, heat flows from a hot body to a cold body in order to keep ds positive. That's the reason in which that occurs. Once the hot body temperature, and of course as the heat flows from the hot body to the cold body, the hot temperature lowers, the cold temperature rises. When they come to the same temperature, thermal equilibrium, then it doesn't matter about heat exchange anymore because ds is 0. I'm at the equilibrium point of balance. And if I tip the scale either one way or the other, there will be a flow to adjust that point of thermal equilibrium. Let's talk a little bit about the bizarre case of an adiabatic process. Remember, adiabatic means dq equals 0. If dq equals 0, then I have all my entropy changes are 0. Delta S of the universe, delta S of the system, delta S of the surroundings. I'm claiming, well, if the system is isolated, there is no surrounding system, really. It's delta S of the universe is 0. Okay, but wait a minute. Let's think about this interesting conundrum that creates. Everybody always says the universe is an isolated system. Everybody always says that the universe is expanding. If the universe is expanding, that is a natural increase of entropy. We will quantify that later, but any object that is bigger is more random, or any object distributed in a larger space has more randomization due to the fact that it is simply in the larger space. And we, again, will soon be able to prove this, very soon. So the universe is expanding, so that means there's an increase of entropy in the universe, which we always hear said, but yet the universe is adiabatic. So what is going on? How can the universe expand, which increases its entropy, yet it is adiabatic, so it has no change in entropy? Quite simply, as the universe expands, it is also cooling. Ever since the Big Bang, the temperature of the universe has been constantly dropping. So as the universe expands, increasing its entropy, it is also cooling, which decreases its entropy. The entropy increase of the expansion of the universe is exactly offset by the entropy decrease of the cooling of the universe. So actually the opposite would be true as well. If I have an isolated system that I compress, compressing it shoves it into smaller volume. Putting it in smaller volume decreases its entropy upon doing that. So I have a decrease of entropy by putting it into smaller space. But simultaneously, upon this adiabatic compression, the temperature of the system rises. As the temperature of the system rises, that's going to contribute an increase of the entropy of that system. So the entropy of the system is increased as the temperature goes up during the adiabatic compression, but it is decreased by the smaller volume occupied during the adiabatic compression. Now the key feature there is adiabatic. Temperature can't be exchanged with the surroundings. So there is a temperature change in the system during any adiabatic process. Before we proceed, let's do a little bit of a reminder about some properties we talked about when discussing ideal gases and their internal energy. First of all, internal energy is a state function, and or prefer saying it another way, it's an exact differential. Being an exact differential, we can write it as we see mathematically, and I talked about what this really means. It means an increment of change of f can be found along a plot of f versus x and y by looking at the slope of f in the x-plane as y is held constant times the increment of change along x, and add to that, since they are independent variables, x and y, they must be independent variables. And if they are independent variables, then I can hold in the other plane x fixed, look at the slope, how f changes with respect to y, while x is fixed, multiplied by the increment of change of y, and I will get, by adding those increments of change in the x and y planes, the total change in f. Now, since internal energy is a function of temperature and volume, I can similarly write du Tv as you see there, the collection of partial differentials, one for t while I'm holding v constant, so that's an isochoric change in temperature. Then I have an isothermal change in volume times the increment of change of volume. Combining those two will give me the increment of change in du. Now the first term of partial differentiation has been defined previously by us. Remember, du is c sub v dt at constant volume because p dv term is 0. So du is equal to dq, and dq is cv dt, and so cv, the constant volume heat capacity, is du dt at fixed v, specifying that particular path. The second term we talked about also previously, du dv at fixed t, we called the so-called internal pressure. It has units of pressure, so it somehow measures how internally, not pushing outward, but internally, something about the way the energy of the system will change as you move the molecules closer or further apart to one another isothermally. Now, for an ideal gas, we have hand-wavingly argued du dv at fixed t is equal to 0. And the argument we can make without mathematical proof yet is that for any isothermal process, energy of an ideal gas is not changing. The only way to change the energy of an ideal gas, since it only possesses kinetic energy, is to heat or cool the gas. That changes its energy. Moving the molecules closer together, shoving the molecules further apart, has no effect on its energy. There's no potential of attraction for the gas particles, so it doesn't matter how close together they are or how far apart they are. You can only change the energy by changing the temperature. As a result, the second term of the statement for the exact differential is 0. So that du is equal to du dt at fixed v times dt. And so what I can do is use the definition of du dt at fixed v as c sub v. So du is c sub v dt for an ideal gas. Now again, if it's a real gas, you have to include a term for that second quantity, the internal pressure. Down the road a little bit, we'll see how to do that. Let's answer another conundrum, that this concept that the internal energy increment of change is equal to CV dt for an ideal gas. And that would be, let's suppose we have isothermal processes where we either expand or contract the ideal gas. So if the ideal gas is expanding isothermally, it would say that since it's isothermal, dt is 0, du is 0. So what it's saying is that gases can expand without expending any energy. And likewise, if I were to contract the gas, gases can contract isothermally without having energy deposited in them. So the riddle for isothermal expansion can be solved by realizing that energy to keep the system isothermal. That means that as it does work of expansion, it is certainly losing energy. So du is negative upon the gas expanding. To keep it isothermal, it must absorb heat. So dq is positive, exactly offsetting the dw, which is negative as an ideal gas expands. Same thing is now true if we say I'm doing an isothermal compression of an ideal gas. The compression of the ideal gas should be doing work on the gas. So that should have a dw greater than 0 as I do work on the ideal gas. However, since it's done isothermally, that means that dt is 0, so du is 0. There's no change in internal energy, even though there's a positive change in work. So what that means is to keep it isothermal, heat energy must be siphoned out to the surroundings. That's the only way it'll stay isothermal. In other words, if I'd have done this adiabatically and compressed it, the temperature would have went up for the gas, because the heat had no way to escape, so the temperature change does go up. Vice versa. If I do an adiabatic expansion, then the gas has to cool, because as the gas is losing energy by doing work, then dt has to be a positive value, since it can't suck heat from the outside as it would under an isothermal process. This slide is a reminder, again, of a topic we've already talked about, but we're going to be using upcoming, so let's remind ourselves. Let's look at an adiabatic ideal gas expansion process. Remember, du is dq plus dw, but if it is adiabatic, of course dq equals 0. And because it's an ideal gas, du is ncv dt. So dw equals ncv dt. And since I've designed a reversible process for dw, I can stick in minus p external dv. Reversibly, that means that's equal to minus nRT over v dv. So now what I'm going to do is, as we do, probably talked about in your quantum mechanics, I separate the variables, move all the t's to the left, move all the v's to the right, then integrate the expressions, assuming n is a constant, it's a closed system. CV, which is a little bit more tricky to assume is constant, but we will say it's for small temperature change, it's independent of temperature. So I will factor the CV out as well. Of course, R is a constant as well. I can integrate both sides of those equations and get NCV ln TF over TI equals minus NR ln VF over VI. Now what I can then do is move the variables to the other side of the equation. Notice the n's cancel, and I get, by removing the ln term, TF over TI is equal to VI over VF to the R divided by CV. And I can then note that the final temperature is proportional to the initial temperature times the ratio of VI over VF to some exponential factor. Okay, so now let's think about that. If I have an adiabatic ideal gas expansion, of course VF is bigger than VI. The quantity in parentheses is less than 1. So TF is less than TI when the gas expands adiabatically. The gas cools as it expands adiabatically. Let's compress the gas. The VI over VF term is bigger than 1. So when multiplied by TI, I get that TF is greater than TI. So if I do adiabatic compression of the ideal gas, the gas will heat as it compresses. This is again because it's adiabatic. Heat can't be exchanged with the outside world, so doing work on the gas increases its internal energy, which raises its temperature when I compress. Okay, now I also could use PI VI over TI equals PF VF over TF to get an equation for the PV relationship upon adiabatic expansion or compression if I so desired. To find the PV adiabat, we begin with the expression from the previous slide, and as I said, we insert PI VI over TI equals PF VF over TF, and I rearrange that to the form of TF over TI, stick that in on the left-hand side of the top equation, gather terms as you see I'm doing there, and I get what I would call a Boyle law looking equation that is varied kind of like the Charles law adiabatic equation was varied on the previous slide for the relationship between V and T. Now I see that PI VI to the CV plus R over CV equals PF VF over CV plus R over CV. Now remember also, for the ideal gas, CV plus R is equal to CP, so that is simply the ideal gas C sub P to C sub V ratio in the volume exponent. What this slide points out is the interesting point that when I was rearranging and solving the equation for adiabatic expansion, I canceled the moles of the system on both sides of the equation. This led to an equation that was mass independent for the change in temperature that the system undergoes upon adiabatic expansion or compression. Here's what that's implying. I could take a little sample of gas and expand it by the same amount, and it'll undergo the same temperature change independent of that amount of gas. Okay, so I could take a huge amount of gas with the same volume change, or a small amount of gas with the same volume change. As long as VI and VF are the same, independent of how many moles of the gas I have, the TI and TF values will remain the same as well in this adiabatic case. Okay, so expanding or contracting this gas when it's ideal, exchange the same amount of heat, and so, or I'm sorry, it doesn't exchange heat because it's adiabatic, excuse me, but because the temperature is intensive, It doesn't matter how much I'm doing it to, I'm going to get the same temperature change in any case. What I show on this slide is simply a plot of PV isotherms versus PV adiabats. The isotherms are in red. They are the Boyle's law equivalent of PIVI equals PFVF, as you can see there. Notice they're both exponential in appearance, but neither is exactly exponential if you want to get down to it. The top curve is the adiabat, so-called adiabat curve, where I have no heat exchange with the surroundings, so temperature is going to be varying along those curves, as a matter of fact, unlike the isotherm curves. And they follow the equation we just derived, and as you can see, there's slight differences. General appearance same, slight differences in the curvature for sure. All right, in this sample problem here, what we have is we have a gas, it's ideal, initially at STP, which of course means its pressure is 1 atmosphere, and it undergoes an isothermal isothermal irreversible expansion. And so of course that means its temperature remains at 273 the entire time. And the way that it pulls off this expansion is that we'll say a piston is pushing in on it at 1 atmosphere initially, and it's pushing back out at 1 atmosphere. But suddenly the external pressure is dropped to 1/3 atmosphere, which means the internal pressure is greater, the force on the inside of the piston is greater, the piston begins to slide out and continues to do so until the internal and external forces are in balance, and that external force imbalance would match the internal force again when the final pressure of the gas inside is 1/3 atmosphere. So we can calculate the volume that the gas occupies. Of course, at STP, it is 22.4 liters. At the final conditions, instead of using a P of 1 atmosphere in the denominator, I will use a P of 1/3 atmosphere in the denominator. And I would get, of course, as you would expect, if I cut the pressure by 1/3, I should triple the volume. So 67.2 liters is triple the initial volume of 22.4 liters. Now ds of the surroundings is equal to minus dq of the system over T. Since the process is isothermal, that means du is equal to 0, so dq is equal to minus dw. And so I can substitute that in, and dw is minus p external dv, which you note I end up with a dq of the system is equal to p external dv. And since this is an irreversible process, I just pull the pressure, I pull that external pressure out, multiply by the change in volume that it undergoes, as you see I'm doing there, and then I divide by the isothermal temperature of 273 Kelvin, and I get a ds of the surroundings of minus 554 joule per K. Now let's think about what that means a little bit. To keep the process isothermal, as the gas expands, it is doing work. So that means as it does work, it should have a negative change of its internal energy. But to maintain isothermicity, that's not really a word, but to be isothermal, I will have to absorb heat from the surroundings in order that the gas can do work as it expands. So that heat I absorb from the surroundings is a exothermic process in the surroundings, which lowers the entropy of the surroundings. Now let's turn to the entropy change of the system. And to do that, we will do dq system reversible over T. Remember, even though the actual path is not the reversible path, the system's entropy is found along the reversible path. And I do that by, again, noting that since the process is isothermal, and it's an ideal gas. du is c sub v dt, dt is 0, du is 0, so dq of the system equals minus dw of the system. So again, I conclude dq is minus dw, which is p external dv, but since I have to use the reversible path in this instance, I will substitute nRT over v dv for that dw term. Notice I'm factoring out, well, I'm not factoring out anything out yet. I can factor out, of course, n and r, and I will have I have a cancellation of the t's, so the ds of the system is nr ln vf over vi. This very familiar expression for isothermal expansion of a gas. This is how entropy changes for that gas upon the isothermal expansion. Notice, as I talked about with you before, when I was discussing the fact that when systems expand, they are increasing entropy. This expression shows that mathematically. If VF is bigger than VI, the fraction is bigger than 1, ln of a number bigger than 1 is greater than 0, so delta S is greater than 0 as long as VF is bigger than VI. Entropy of a system increases as volume increases. If VF is less than VI, the fraction is less than 1, ln of fractions less than 1 are negative, delta S is negative if VF is less than VI, stating again that I have a decrease of entropy if I compress a system to a smaller volume. Okay, now when I put numbers in, I find a delta S of the system of 9.13 joule per K. Now remember, I essentially used a irreversible path to find the entropy change of the surroundings. I'm using the reversible path to find the entropy change of the system. And remember, as I talked about, maximum work is done along the reversible path compared to the irreversible path. So there's more entropy for the system because I used to use the reversible path than there is in the surroundings where I used the irreversible path. Now, if this was a compression, then as I said, the work of irreversible compression is minimum work. I would do more for the irreversible compression. So that would be an overall ds of the universe of a negative value instead of a positive value. Notice when I do delta S of the universe, for this case, I'm having negative entropy in the system. Negative entropy of the surroundings, 5.54. Positive entropy of the system, 9.13. Overall, a positive entropy. What this is saying is spontaneously, taking into account the system and surroundings, spontaneously, the universe is randomizing as the gas expands. Let's take a look at a sample problem where I calculate the entropy change when I deposit 65 kilojoules of heat into 125 grams of ice. Of course, I have a phase change from the solid to the liquid, and the enthalpy of fusion, which is the amount of heat, the latent heat as we call it, to melt ice, is 602.02 kilojoules per mole. Okay, now that's a positive quantity. Of course, it's endothermic to melt ice. It's an intensive that I can scale by the amount of ice I have present. Okay, and also notice this is the latent heat, meaning the temperature does not change as the ice melts. The temperature remains at 0 degrees C or 273 Kelvin as the ice melts. So first, let's determine if I have 125 grams of ice, how much of that heat of the total of 65 kilojoules I'm depositing into the ice, how much of it is really necessary to melt 125 grams of ice. So I find the moles of ice and then I multiply by the kilojoules per mole of heat, and I find it's going to take 41.8 kilojoules of heat to melt 125 grams of ice. So what happens to the rest of the heat? It doesn't disappear. It warms the ice from 0 degrees C up to some final temperature. How can I find the final temperature that it heats the water up to? Well, I say Q is N Cp delta T, the constant pressure heat capacity of the liquid water, which I can look up in the table somewhere, and I do look that up somewhere. I find that the value of the heat capacity of ice is, I'm sorry, not ice, the heat capacity of liquid water is 75.29 joule per K per mole. So I find then the delta T is Q divided by N Cp, and so the remaining heat, 23.2 kilojoules, I convert to joules. Then I divide that by the number of moles of ice I have present and the constant pressure heat capacity of that ice. And I find that the final temperature, or I'm sorry, the change in temperature will be 44.4 Kelvin. And since the ice started at 0 degrees C, or 273 K, I find the final temperature to be 317 K when I add the remaining heat into the ice. Now that we know how the temperature will change, let's calculate the entropy of the process of putting 65 kilojoules of heat into 125 grams of ice at the phase boundary. Remember, ds is equal to dq of the transition over t of the transition. So I will substitute in delta H for the melting of ice of, as we see there, 41,800 joules divided by my temperature of the transition, which is 273 Kelvin, and I get a plus 153 joule per K for melting the ice. Significant entropy change of melting the ice because, of course, solid ice is much more ordered than liquid water, so that there's a big entropy change as I melt all that ice. Okay, now what do I do to find the entropy change during the heating of the water? Well, again, ds is equal to dq over T, and for constant pressure processes like this melting ice, that will be NCP dt. And here I have to integrate Cp dt over T. I pull the Cp out, as a matter of fact, and integrate NCP times the integral dt over T, which of course is ln of T. So I stick my numbers in and I get the entropy change of adding the heat into the liquid water of 78.1 joule per K. Notice that's about half as much entropy change as melting the ice. So the total entropy change will be the entropy change of melting the ice plus heating the liquid water. That's a total entropy change of 231 joules. When we have systems at equilibrium, remember, since we can partition the universe into a system and surroundings if it is isolated, then at the point of spontaneity for equilibrium, or the naturally occurring process of equilibrium, states that delta S of that universe in the Clausius inequality takes the equal sign, so delta S of the universe is equal to 0. And of course, since the universe is partitioned into an entropy of the system and the surroundings, and that total entropy for an equilibrium process is 0, that means at processes which come to equilibrium, the entropy change in the system is exactly equal and opposite to the entropy change of the surroundings.